sweat a lot.
Oh, I bet, yeah. Well, that's really made to seal you in.
Yeah,
Right.
it works pretty great.
Switch cameras. You'll notice that there are some exercises, and my expectation is basically that you will do them all. Now, I should explain what I mean by do them. Sometimes there will be like multiple exercises that they're the same thing. It's just that the data changes. You know, do certain things with this matrix, and then there's 3 more where you practice again. By my way of thinking, if there's 4 of them listed and you do 2 and you think, oh, I got it. Well, okay, then move on. But you should be doing more than just reading each one. You should actually be thinking about it. And if you come across an exercise that you don't know how to do, it means one of 2 things. Number one, you have some work to do. You know, figure out how to do that. And one of the things you can do is ask me. I don't mind helping at all. The other possibility, of course, is that somehow it got mangled in the process of getting it from my idea or copying it from some other source and putting it in the notes. So if there's one that just seems completely unworkable, well, you know, don't kill yourself over it. Send me a message and say, hey, this doesn't seem to be working out. Could there be a problem here? And I'll check. And as people do that, it helps get the bugs out of the system. So on this week, normally I would like to give a turn-in assignment on this day, on Thursday, which you would then submit on after the weekend on Tuesday. I decided not to do that this time because the material is getting quite a bit deeper. I think it sort of went up a notch a little bit last time, and it goes up again today. So I thought, you know, it would really be better if, especially over this weekend time, if we don't have an official hand-in assignment and everybody has freedom to consult with each other, send me email or whatever if things are going wrong, and we sort of get you moving on this first. And then I will, then my plan is to give a turn-in assignment on Tuesday, which you would submit on Thursday. Okay, so that's the plan for this coming week. So you should have things more or less hashed out, not all written up pretty, but you should generally know how to solve the problems when you walk into class on Tuesday. Now, if there is a problem with scheduling, you know, if someone, and I'll hold the class on Tuesday. If it turns out that, you know, we've got people that are working full-time and coming here in the night, and, you know, they don't have a lot of time, so then we can look at some flexibility on deadlines. But I do want you to keep up on the homework, please. And I say that for your benefit. If you get behind, you will find that catching up is unbelievably difficult. So that's probably all I need to say about that for now. Tonight, oh, I want to say something about the recordings. Last time when I did the recording here in class, it was the first time I used the classroom equipment, and it actually worked pretty well, except the recording as it was here locally, the sound quality was so awful, I thought it would be completely unusable. But since that was the only recording I had, I uploaded it to YouTube and linked it to Blackboard. And then I checked it after, I don't know, the next day or 2 days after I posted it, and it was actually pretty listenable. I think that YouTube might have run some filtering or something on it, or perhaps it was just the the playback equipment that's available to me in this room, because I did it right here before I went home. So so I thought, well, it seems to me to be working, so I'm going to stick with using the camera and the mic that's built in here in class. If that is not working for someone, please let me know, because I do own a headset, and if by wearing that you get audio that you can listen to and you're making use of it, then I will switch if that helps you. But I won't if I don't get a prompt. So please let me know about that. Last thing I want to mention is the thing I have noticed about this class, maybe that strikes me first, is how quiet you all are. And I think a large part of that has to do with our format. You know, at least half of our class members are not coming here. So that really ties me down to this spot. And it's really hard to make the class interactive because I don't hear people that are coming in remotely. So probably starting on Tuesday, I'm going to deliberately be setting aside time at the beginning of class to answer questions. So have your questions ready, and you know, I will try to help you. For those of you who can stay after class as well, and it doesn't matter whether you're online or in person, I do hang around for a while because I have to process the video. So, and once I get that started, you know, I'm waiting for it. So if you want to ask more detailed questions, then I'm happy to help you out. All right, I think that's it. So I'm ready to launch. This is section 1.4 from the notes posted to Blackboard. I think as we move deeper into the subject here, you may find the notes to be more useful. I don't know if they'll be useful to you in class. That's something that's totally up to your judgment. I don't care what you do to learn in here. Just do what works. But I post them because I really don't have a textbook I'm following. And if there's no written record of what I'm thinking, then what do you do when you get stuck, right? So I'm fairly conscientious about trying to get notes that are that explain the approach I'm taking to the subject. And then if you haven't checked it out already, you should do so. These sheets that I write on, I then fix them up if they're, you know, it's got big problems I know about. And then I scan them and post that to Blackboard too. So please, please do make use of those resources in as much as they're helpful. None of that is required. It's just resources. Oh, and last thing I should say before I launch is I probably should have been more forthcoming with you last class time. I realized after it was all over, I was having so much trouble with arithmetic. I was quite ill over the weekend, and I actually spent, where was it? Saturday night in the hospital. So I was still not firing on all cylinders, and I couldn't do arithmetic. I don't know why. So that seemed to be better after my antibiotics had a couple of days to work on my issues. So I hope we're good to go now, but I don't know, as much of I felt okay when I came in here last time too. So anyway, that's it. So here we go. A lot of this is just kind of preamble here at the beginning. It's so that the notes make sense if you pick them up after the class. And there's really not a lot of reason for me to read through them, other than to say the context here is I'm assuming everybody has worked with vectors in some way before they get to this class. And, you know that, I think even in high school, I got a little taste of 2- and 3-dimensional vectors in my high school physics class or something. We learned about dot and cross product and thought we were terribly wise as a result. And I suppose compared to the world population, we were, it was probably puts us pretty far out in the distribution, but there was a lot more to learn. That's the context here. Where we're starting with vectors, we're going to be thinking primarily of sort of R2, that means the 2-dimensional real numbers, R3, 3-dimensional real numbers, having 3 components or 3 entries in a vector. And how do you work with those? Just exactly the same way that you always have. If you want to add a pair of vectors, you add up the corresponding entries. And if you want to multiply a vector by a scalar, well, you multiply all the entries by that scalar. And that's what you've been doing, right? So presumably that's not too much of a surprise. Okay, now, just a note on how we express these things in writing. Sometimes, usually officially, what we have in mind with a vector in linear algebra is a column matrix like this. But in fact, it doesn't matter. This and this and this are all clearly indicating a 2-dimensional vector with components that are A and B. So we do move back and forth a little bit, and usually we're not terribly careful about it when we do. So if that's confusing at some point, you're always welcome to say, hey, wait, I don't understand what's going on here. It's probably a good idea to ask those kind of questions. But the problem is I've been doing it for so long, I won't even anticipate that it might be a bump in the road for you. So I really do depend on you asking if something like that is not so easy.
Is that a little P above the bracket
Yes,
there?
and that means transpose. So if I write a matrix like this, 1, 2, 3, 4, if you put a T in the superscript position, it means interchange the rows and columns. So the first row becomes the first column, and the second row becomes the second column, and you get this. So what would happen if you took, let's take a 3-dimensional, because the more pieces, it's easier to see what's going on. What would happen if you took the transpose of that? Well, you would switch that first row. It happens to be the only row, but it's still the first row. Turn the first row into the first column. So it means basically turn this into a column vector. Okay, so that's the meaning of the T. And there, the last lecture had it tucked in there somewhere. That transpose was defined, and also symmetric matrices were defined. A matrix is symmetric if it's equal to its transpose. Okay, so thank you. Any other things before we get rolling here? Okay, tonight we get our first taste of writing little bits of proofs. So I am going to, first of all, give you the idea of what closure is, and then I'm going to give you at least a sketch of a proof that, let's say, R3, the 3-dimensional vectors, are closed. Okay, closure means, first of all, it has to be closure under some particular operation. So there's, I don't need to read all this now because I'm essentially saying all that information. There's going to be closure under vector addition and closure under scalar multiplication. So what that means is this. If I start with a 3-dimensional real vector, if I start with a pair of them and I add them up, I get another 3-dimensional real vector. And if I start with a a scalar and a vector and take the scalar multiple, once again, I get back the same sort of object that I started with, a three-dimensional real vector. Now, you might think, well, of course you do. Yeah, but think about this even. You saw this in introductory physics. What happens if you take the cross product of a couple of vectors? Do you get, well, I guess you do get another three-dimensional vector there. Dot product, that's the one I want. Suppose you take the dot product of a couple of three-dimensional vectors. Do you get another three-dimensional vector? No, you get a scalar, right? So it is not guaranteed that operations that you define on a vector space are going to give you results that stay in that vector space. And so that's what we're saying here. If you add two vectors in the vector space, you get another thing in the vector space. If you take a scalar multiple of a vector in the vector space, you get another vector back in the vector space. Now the proof, once you have the idea, the proof is just tedious because the idea is so simple. But the main purpose here is to show you how you would actually write something like that. So what we want to show is that R3 is closed under vector addition and scalar multiplication. So I will do vector addition first, and you don't have to do it this way, but it doesn't hurt to put some order on your work. So I'm just writing a heading here. Vector addition, what I want to show is that R3 to show R3 is closed under vector addition. So what have I proved so far? Nothing. I've just sort of given my subject heading. You know, I'm going to try to prove this, okay? So let U, and some notation here really helps. So I'm gonna use the notation, but I'm gonna explain it as I go. What I want to do is say let U and V be vectors in R3. So I write that English word there, and then that means is an element of. So what that mathematics says is let U and V be two vectors in R3. Then U, and now I'm going to use that sloppy notation where I said we sort of sometimes switch back and forth between horizontal and vertical format just because it's convenient. So all I'm saying is, well, what do vectors in R3 look like? They got to have three numbers in order. We'll call them U1, U2, U3. V equals V1, V2, and V3, where, and I got a list of 6 things. U1, U2, U3, V1, V2, and V3 are all elements of the real numbers. Then, what is the vector sum? UV equals U1 plus V1, U2 plus V2, U3 plus V3. Well, we can see that's back in R3 because, and I can summarize now, it's true for each of 1, 2, and 3. UI plus VI is a real number. Okay, now we get all kinds of notation here, but the ideas are simple. Pick a couple of vectors. Each of them must have 3 entries, and those 3 entries in each vector are real numbers. What happens if we perform the vector addition? Well, we get, once again, 3 components from the definition, and this is a sum of real numbers. so it's a real number. This is a sum of real numbers, so it's a real number. And this is a sum of real numbers, so it's a real number. Well, that's all I need. If I got three numbers in a row in order, that's what we mean by a three-dimensional vector in three-dimensional real space. Okay? Does it make sense? All right. Well, now I have to look at scalar multiplication. Well, actually, I should make the conclusion. So what I did was this. I picked any two vectors in R3, added them together, and I got another vector in R3. So R3 is closed under vector addition. And that's half of the proof. All right. How about scalar addition? Scalar multiplication. Scalar addition. And this is going to say to show that R3 is closed under scalar multiplication. Okay, so we're going to do basically the same thing we did in the first part. In that case, to look at a sum of vectors, you have to pick two vectors, you add them up and check to see that they land back in R3. So we're going to do the same thing here, except with scalar multiplication, we need a scalar and we need a vector. So let K be a real number. That's a scalar. And I'll use V and this time I'll use some words, but essentially it's what I said here, right? Only now I got two sets going on, R and R3. So let K be in R, and I could just say let V be in R3, but I'll spell it out with English. So if someone is struggling with the notation, they have something to match to down here. Let V1, V2, V3 be a vector in R3. Then K times V equals, and all we have to do is apply the definition. And in fact, all we can do is apply the definition because we don't have any other theorems to work with right now. So that's K times V1, K times V2, K times V3. Since, now last time I used this shorthand notation tried to represent all three subscripts with one equation. This time I'll spell it out and show you an alternate way. You could write it this way. Since KV1, comma, KV2, comma, KV3 are all real numbers, and I could have just said this, are in R, or elements of R. Then, well, I've got three real numbers stuck in my triple here. Well, that's what we mean by being in the vector space R3. Then KV is in R3. So R3 is closed under scalar multiplication. And that's it. Now, if this is your first exposure to proofs, you'd probably be inclined to spend several minutes after class to sort of let this sink in, read it over. Why did he write this here? Why did he not do that there? And at the end of that session of mathematical meditation, you'll say, all he did was say if you add two vectors, you get another vector. And if you take a vector times a scalar, you just get a vector. You got it, okay? It really is that simple. But we're spelling it out in technical detail. Okay. Anybody want to ask a question before we move on? That air conditioning is really effective, isn't it?
Yes, yeah.
Oh, you're sitting right there. Please feel free to move around if there's a more comfortable spot.
Oh, that's fine. I got warm tea.
Oh, I see. Okay, now, the reason that people actually write proofs about stuff like that is that not every set of vectors is closed under vector addition and scalar multiplication. So here is an example of a set of vectors that is not closed. This is the set of two-dimensional real vectors that has this property. Its entries, the entries in the vector are strictly positive. Well, now I want to show that this is not closed. So let V be 1, 1. That's certainly in the set. Now, if you notice, I'm taking a totally different tack here. The first time, I just took a general vector U, a general vector V, a general scalar K, went through all the machinery and said, aha, it works, just like we know it, it works. But in this case, I'm starting with something specific. Why? Because to show that it is not closed, all I have to do is give one example. To show that it is closed, I have to look at every possible way of adding two vectors. So just one counterexample is satisfactory. So let V be 1, 1, that's certainly in the space, comma, and minus 2, well, that's a scalar. And I suppose I should give that a name, K. Then KB, that's a scalar multiple, equals minus 2 times the vector 1, 1, which is minus 2 minus 2. And guess what? We jumped out of the set, right? This is the set of vectors whose components are strictly positive. And I have now found a scalar multiple of a vector in S that jumps out of S. So to say it's not in S, it's like, it's the same deal as when you make a not equal sign. That's not an element of S. So S is not closed under scalar multiplication. Now, vector spaces have this property. They must, absolutely must be closed under vector addition and scalar multiplication. So I have just proved that S is not a vector space. Why? Because it isn't closed. There's other things about it too, you could say. They all have to have a zero vector. Well, does this one? No, it doesn't. So that would be another way to prove that it's not a vector space. Doesn't have the zero vector. For every vector in the space, the negative of the vector has to also be in space. And that fails here as well. So there's multiple ways of proving this, but I just showed that it's not closed because that's the only property we've talked about right now. Okay, now let's take a look at this one. T is the set of two-dimensional vectors where you have the cosine of T for the first entry and the sine of t for the second entry. So maybe I could let someone try to suggest what would go wrong here. And we're going to look at closure because that's the only thing we're really working on right now. What could we argue? Just not a proof, just like a quick example. Can you think of a couple of vectors we could add that would jump us out of the space, or a vector times a scalar that would jump us out of the space? My suggestion is to start thinking of trying to come up with a vector that's in the space. Could we get that far even? Pick a value of t. What's a nice t?
0.
0 is a great one. So if we take t to be 0, by the way, we're started with this proof now. Let t be 0. What will this vector be? Cosine t sine t becomes cosine of 0 is 1. Sine of 0 is 0. So we know that 1, 0 is in the space. Now, could we think of a vector we could add to that? Another vector in the space we could add to that that would jump us out? Or could we think of a scalar multiple that would jump us out? Anything that would produce in either entry that could not possibly be a cosine or a sine. Idea? I think you probably have a great idea, but I can't hear it. I'm sorry. Yes, let's multiply it by something that's greater than 1. Another possibility, we could multiply it by something that's less than -1 would also work. So I like this idea. So you got a favorite number greater than 1? How about 2? Let's take 2. Let's give this thing a name. I'll call that v. 2v is equal to 2, 0. Now, do we have a problem with the 0? Could that be equal to the sine of something? Well, sure, it was before, right? It's the sine of 0. What about 2? Is 2 equal to the cosine of anything? Cosine and sine are trapped between plus and -1. So this is not equal to cos t sine t for any t. Therefore, 2v is not in this space of which I call capital T. So T is not closed under scalar multiplication. And that's all we need. If it were a vector space, it would be closed under both operations, vector addition and scalar multiplication. This one's a little more challenging. I think what I'm going to do is write on the back of the page, A2A, 3A. So let's just write down the recipe. We're thinking of, this is a subset of R3. And the idea is you could just set A to be any real number. Well, let's take some examples, okay? So we start to get a handle here on what we're looking at. If A were 1, then that becomes 1, 2, 3. That thing is an element of, what's it called here anyway? S. Is in S. Another one, well, what if you took A to be 2? Then you'd have 2, 4, 6. That's in S. If you took A to be 0, then you get 0, 0, 0. That's an S. That, by the way, that's a good sign. Remember I said that every vector space has to have the zero vector in it. I also said if you have a vector in the space, it's negative also has to be in the space. What about this one? If you took A to be -1, -1, -2, -3, is that in the space? Well, yeah, it's the negative of that, and it is in the space. So this is actually checking out so far. Okay, now the idea is, what if we added a couple of these things together? Would it preserve this pattern? Well, give it a try and see what happens with your examples. And by the way, you don't have to be right in general. Just tell me what happened with your examples. It seemed to work with these, or, oh, I think I found a bug. Well, what do you think? If I add a couple of vectors that have this pattern, something, 2 times the something, 3 times the something, I add them together to get another thing that has that pattern. Does it work here? Yeah. 3 times 2 is 6, 3 times 3 is 9. This is starting to look pretty good. All right, so in that case, what we're gonna do, whoops, excuse me. What we're gonna do is we're gonna try to write a proof. So let U and V be in this space S. Okay, what does it mean to be in S? Well, it means you have to be obeying this pattern. The first entry is some number, and then you have 2 times that number for the second entry, 3 times that number for the third entry, and you can call those numbers whatever you want. So how about this? U is equal to, I'll just start with my A. There's no real compelling reason to do that. I just have A on the page already, so I like it. I'm going to stick with it. And V, well, V presumably might be something different because I was born into an English-speaking family. I'll use B next. But of course, there's no good reason for that either, other than convenience. Okay, and so now I have 2 vectors that are in S. Then this has to be true and this has to be true. Why? Because they're in S. Everything in S obeys that pattern. Then U plus V. Okay, what's the first entry of U plus V? This is the easiest question of the 3 that are coming down the pike here. So you should take this one. What is it? A plus B. What's the next one? This is deep mathematics, isn't it? I hear sounds, but not words. Yep. And at this point, the pattern's been established, so I'll quit bothering you. And then you could say, if you really were being pedantic about this, you'd say, well, look, I've got a real number here, A plus B. I have 2 times that real number in the second entry and 3 times that real number in the third entry. And that is right back in the set S. So S is closed under vector addition. Good start. By the way, if it's closed under vector addition, it's got a good chance of being closed under scalar multiplication. Not guaranteed by any means, but at least it's worth checking out. All right, so for the second part, let K be a scalar in the real numbers. And I'll just use a vector I already have defined here. U be ABC. No, it's A, 2A, 3A. Then K times U equals KA. Well, K times 2A, but of course that's the same as 2KA. And K times 3A, but that's the same as 3 times KA. And you can already see that the only thing left to make it a proof is to put parentheses on here, right? We have the first entry, then the first entry doubled, then the first entry tripled. That's back in the set S. So S is closed under scalar multiplication. So it will turn out, and I haven't actually given you all the theorems yet, but this is good enough to conclude S is a vector space in its own right. And a subset of R3. So it's a vector space, R3, that lives entirely within the vector space, R3. Okay, well, that's it. That takes care of that. Did all this show up on the screen here? Yeah. Okay, so that's that takes care of this one right here. Is this closed? It is closed under vector addition and scalar multiplication. All right, now, are there any more vector spaces? Well, of course there are. You could have any number of entries in a vector. You could have n entries, where n could be, well, it could be 2 or 3. That's what we've worked with already, but it could be 100,000 too. So, and how do you do vector addition? Just the same as you do in R3. How do you do scalar multiplication? Just the same as you do in R3. So those are the vector spaces Rn. And I won't say a lot about that. We'll end up working in that a lot, but presumably that's, not much of a generalization of R2 and R3. And by the way, these are sometimes called the Euclidean spaces. At least they're the Euclidean spaces with the usual dot product defined. Okay. Now, I do want to say a word about high dimensional vector spaces, because sometimes people ask the question, oh, wait a minute, this is getting so crazy abstract. I can't think of 4-dimensional space, much less 50-dimensional space. Why would we study such a crazy thing? Well, let me give you an example. Think about sound waves that you are listening to right now, and particularly if you've joined us by Zoom, the way you're getting them is actually going through this mathematical system, probably. Another thing you could think about would be just mechanical vibrations. That's certainly something of interest to engineers, right? If I tap on this, I set up some kind of a vibration in this piece of plastic here, and you could hook up some instrumentation and follow that, and it'd probably be a fairly complicated waveform, but there is one. Okay, now what if you wanted to represent that mathematically by something other than a graph? It turns out that for pretty much any kind of a vibration, whether it's sound or otherwise, you can represent it by an infinite series composed of cosine functions. And what it will do is get you a little segment of, you have a very complex waveform. It'll give you a little segment. I should put my hands down here. So it'll give you a little segment of this very complicated waveform that goes on for a long time. And why? Because, well, the cosine is is just going to repeat itself every 2 pi units, but it'll give you a picture on either zero, typically it's 0 to pi is what people are looking at, or minus pi to pi. And then what you do is you just chop up the waveform into sections of length pi or 2 pi, and you do this process for each little section. Now, as long as you're willing to use an infinite series, and your wave isn't too complicated, doesn't have too many discontinuities, you actually will get a perfect representation of it. And so that is essentially a vector space. What you are doing, oh, did I not write that down here? You could say, well, we know what these cosines are. They're 1, then cosine of t, cosine of 2t, cosine of 3t, et cetera. So all of the information is contained in the coefficients. So there you go. That's an infinitely long vector. That's an infinitely high dimensional vector space. And certainly mathematicians as well as engineers and physicists are very interested in these things. Now, of course, if you think about sound now, these coefficients in here correspond to higher and higher frequency components. Well, if you think about the human ear, after about, what is it, 20 kilohertz or something, even young ears like yours can't pick up those sounds. Mine probably does not go that high anymore, because actually this is true. The higher frequencies are lost faster as a person ages. So I probably cannot hear at that range. You probably can hear something up there. But after that, you don't care about those components because they're not audible anyway. So now you just have a finite sum of cosines. And this might look crazy wild, like I'm going to have 20,000 terms here. No, it turns out that for good sound reproduction, around a dozen terms is pretty good. So how do you digitize sound like this? A cosine series would do it. And then all you got to do is record the coefficients. And then your computer grabs the coefficients, it constructs mathematically, it constructs that short series, it plays it for that little short time, and it says, okay, I'm at the end of my interval, and now it grabs the next series, the next collection of coefficients, and makes the next series, and it plays that. And if you have like a dozen terms, it's really good quality sound reproduction. As a matter of fact, I did this for a class one time. I found out what the frequencies were in the sounds. This was back in the old days when we had telephones that were, the handsets were bigger than this calculator. And when you push on the buttons, you would hear characteristic tones. And so I constructed it with this is called the Fourier series, constructed with the Fourier series and played it, and people said, whoa, that's a telephone. I said, see, it doesn't take, and I think I only had two or three terms in my series. So these are definitely practical. That's the point of this, okay? Very, very practical to be able to work with high dimension vector spaces. So people do it all the time. And if you have listened to music today, how was that digitally recorded? Essentially like this. Of course, there's details that get involved with the engineering, but essentially this is the strategy. Okay, now we're ready to start the discussion of dimension and basis. So what do we mean when we look at, say, a vector like this, 1, 2, you could say, well, that came out of a two-dimensional space. And I say minus 2, 0, 5, that came out of a three-dimensional space. Well, what exactly do we mean by the dimension of a vector space? That's where we're headed. And it turns out that the answer to that question is, well, the dimension of a vector space is the number of vectors in any one of its bases. Well, that was helpful if we knew what a basis was. So now we have to define what a basis is. But in order to define what a basis is, we have to know what linearly independent vectors are, and we have to know what the span of a set of vectors is. So we're going to be looking at linear independence and span, because that tells us what a basis is, and a basis tells us what dimension is, and that's why I asked the question. I just wanted to have an outline to follow. Okay, so that's what we're working on. What is the standard basis for Rn? Well, it turns out, how about if I do R3, you know it already, you just might not know that it's called the standard basis. It's this. And in high school, I think I was taught to call those vectors I, J, and K. And you know, it's perfectly good system. In Euclidean spaces, we typically call them E1, E2, and E3. Why? Because, well, what if you're working in a 25-dimensional space? You're going to run, well, 25, I guess would be okay. What if you're going to work in a 27-dimensional space? Well, you run out of letters, right? So, if you had Rn, its standard basis is E1, E2, through En. And what do they look like? They look just exactly like these. Ek is the vector that has all zeros in it, except it has a 1 in the kth entry. All right, so now, once you can see what a basis is, you can see, oh, look, 1, 2, 3, there's 3 vectors in the basis. That's why we call it 3-dimensional. This will have n vectors in this basis. That's why we call that n-dimensional. That's where we're headed. Okay, linear independence and span. We want a precise and terse definition of basis. Now, I can tell you the definition right now. It's really simple. A basis of a vector space, and by the way, don't just quickly scribble this down. It's on the following pages. A basis of a vector space is a set of vectors from the space that is both linearly independent and spans the space. That's the answer. And the answer is easy. The harder part is explaining what does linearly independent mean and what is the span of a set of vectors, and also how do you compute the span of a set of vectors? What calculation can you do to show that a set of vectors is or is not linearly independent, etc. Okay, we start with a linear combination. Let V1 through Vn be n vectors and C1 through Cn be n scalars, all from the same vector space. A linear combination is simply a sum of this form. It's a scalar times the first vector plus a scalar times the second vector, etc., until you've used up all your vectors. That's a linear combination of V1 through Vn. It's just a sum of that form. Now, in order to make this concrete, let me put it in a sentence. The vector 3, 2, 5 is a linear combination of the standard basis vectors E1, E2, and E3 because 3, 2, 5 is equal to 3 times the first vector plus 2 times the second vector plus 5 times the third standard basis vector. And you think to yourself, well, yeah, that's really easy. That's right, it is. That's why we picked that to be the standard basis.
Scooch it over to the
Oh, sorry.
here, please.
Yes, thank you. Okay, so 325 is a linear combination of 100, 010, and 001. How do I know that? Because if I take 3 times the first one plus 2 times the second plus 5 times the third, I get this target vector 325. Now, that is going in one direction. If these vectors were not so simple, then it might be a whole lot harder to figure out whether there are coefficients here to make this work. And I'll show you how to solve that problem in this lecture. Okay, now, essentially, what we want to do is to be able to list a set of vectors which will cover the whole space. In other words, by using these kind of sums, we can build anything in the vector space. But we want to do it in the most economical way. So if 3 vectors will work, we don't want to give a set of 5. So what we want to do is avoid redundancies in our set. And that is what linear independence will do for us. So let me give you an example of redundancy so you know what I'm talking about. Take a look at this vector right here, 2, 3, 0. Can I build that? Can I build a linear combination of these 3 given vectors so the linear combination of these 3 is equal to 2, 3, 0? Well, you probably don't need long to think about it, right? You'd say, well, sure. I mean, just do what you did in the line above. And you got this extra vector you don't need, but that's fine. Multiply it by 0. And if that's what you were thinking, you would be right. That is true, that 2, 3, 0 is a linear combination of these 3 vectors, and I've just zeroed out that one. The problem with including, so in some sense, this extra vector is redundant, right? I don't need it in order to get here to 2, 3, 0. However, notice it's not the only way of doing it. It would also work this way. 1 times 1, 0, 0 plus 1 times 0, 1, 0 plus 1 times 1, 2, 0. And I think that works. First component will be 1 plus 0 plus 1 is 2. Second component will be 1 plus 2 is 3. And third component is clearly 0. So it does work. So this is sort of like a city where, you know, locations and addresses are not matched in one-to-one fashion. Given an address, it'll take you to a location, but there's other addresses that would take you to the same location. We would think this is not a good way of coming up with addresses, right? Very, very hard to figure out, you know, you're given two addresses, well, are they pointing at the same place or not? It could be really quite difficult to tell. And the thing you could notice about this is I could subtract these 2 lines whenever this happens. Whenever you can give 2 different addresses to get to the same vector, it will also be true that you can give 2 different addresses for the 0 vector. So 2 minus 1 is 1. 3 minus 1 is 2. And 0 minus 1 is minus 1. This is the evil situation that we want to avoid. The 0 vector, of course, can always be built this way. You just take 0 times all of the vectors in your list, right? So what I've got is 2 different recipes for the 0 vector. If you can, oh, I didn't have it in the right spot. I'm very sorry. If you can write 2 different recipes for the 0 vector, then you've got some redundancy in your set of vectors. And in this case, that 1, 2, 0 is just not needed. We could throw it away and reach anything that we can reach with the first 2. So we would say that this set of vectors is dependent. Whoops, I need a P there. Dependent is dependent, and what we mean is that this one is equal to a sum of those 2 there. If I take 1 times the first plus 2 times the second, I get that third vector, right? So that third vector depends on the other 2. It turns out, in fact, that the middle vector depends on the first and the last as well, but that's another discussion. So this is bad. We don't like this. Is there, we call this a non-trivial This is a trivial linear combination. All your coefficients are 0. This is a non-trivial linear combination. If there's a non-trivial linear combination that adds up to 0, that we do not like. And we say there's a dependency in the set. You could eliminate something in the vectors you're working with, and you would have just as much power, but you'd have more simplicity. Okay. I'm now ready. I go through all of that calculation to prime your brains for this simple statement. Linear independence. V1, V2 through Vn, these are vectors, of course, are linearly independent, none of them depend on the others, this is an old mathematical abbreviation. It means if and only if. IFF. V1, V2 through Vn are linearly independent if and only if 0 equals, now that means the 0 vector, C1 V1 plus C2 V2 plus Cn Vn forces C1 to be equal to C2, to be equal to C3, etc., all the way out to Cn, which is equal to the 0 scalar. So in other words, the only linear combination of the vectors that gives the 0 vector is the trivial linear combination. I don't know why. Sometimes I pause for a long time when I'm trying to remember the names of my children. But I remember this day sitting in linear algebra class when I was an undergraduate, and my professor just wrote this thing or something logically equivalent. And I said, no, wait a minute. If this is always true, if you set all the constants to 0, of course it adds up to 0. And he said, correct, but the point of this is there can't be any other way of getting 0. And then the light turned on. I said, oh, I see the problem. Yeah. So if you want an example of linear dependence, this is it right here, right? This is dependent. This set is dependent because you have a non-trivial linear combination that adds up to 0. And I'm going to copy that into examples here. I'm not going to rewrite the whole thing, but 1 0 0, back on the screen, 1 0 0, 0 1 0, and what I have there, 1 2 0 are not independent, which is a double negative, i.e., they are dependent. On the other hand, well, let's give an example that it really is quite simple, but that's good because you can see right through it. This, the standard basis of R3, is independent. And that is actually fairly easy to prove. Let's try this. C1 times 1 0 0 plus C2 times 0 1 0 plus C3 times 0 0 1 equals, well, let's just do the math. This will have C1 in the first component, and it gets a 0 from here and here, so those don't contribute. This will have 0 in the middle, 0 in the middle. This will get C2 in the middle. And this will get C3 at the end. And this is supposed to be, you set it equal to the 0 vector, and ask, does that force C1, C2, and C3 to be 0? Yeah, it does. It's the only way to get the 0 vector out of this formula, right? Okay, well, from shallow examples, the math is starting to get a little deeper. So now we can start asking this question about just a random set of vectors. Of course, they should all be from the same vector space. So I've got three-dimensional vectors here, 4 of them, and the question is, are these linearly independent or not? And if they are not independent, could we find a subset that is? Well, let's answer that question first, that first question first. And I'm going to write this in the standard matrix format because it'll help you see why what I'm doing is going to work. And once you see this once, you know the recipe. So I am now showing you the secret key to solve infinitely many possible homework problems. Though of course you'll only have time to solve finitely many. So I take a linear combination, a general linear combination, I add it up and set it equal to the 0 vector. And I want to solve for C1, C2, C3, and C4. Well, this of course is a crazy mess. However, we have a nice compact way of writing systems of equations like this, which after all is why we have been studying them. Like so, right? So how do we solve such things? Well, we find the row-reduced echelon form of this matrix, and you could append a 0 column out here if you wanted to, and you read the solution. And we just want to know, we do know one solution, you set all of these equal to 0, right? The trivial solution is always a solution to a homogeneous system of equations. We have language for this now. The question is there another solution? And well, that we can find out with a calculator, except I'm going to show you the calculator is going to choke on this, but I'll show you how to trick it into doing it anyway. Okay, I want to edit a matrix, and this is what, a 3 by 4. Oh, I wonder if I already have, nope, I don't have this one in here. So 1, 1. By the way, if you do this by Octave or MATLAB, you don't need any trick. It just does it. Okay, so you might not need to, but for me, it is very good advice to step out of here and display that. Aha. I bet you I forgot to quit. Okay, is that my matrix? 1, 1, 2, 1, 0, 1, 1, 1, and yes, it is. So what I would like is the row reduced echelon form of this. And I just made this discovery. I don't usually use calculators when I've got Octave. It's so much nicer. But some people in here will. So I thought, okay, remind myself of how to do this, and I press enter, and oh, it worked this time. Oh, how interesting. Oh, maybe if it's got too many rows. Anyway, we'll get there later. So we don't need to do anything. Here is the row reduced echelon form. 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1. Now, what I did not put in the calculator is there's a column of zeros over there, right? So if you're used to looking at it that way, that's what your row reduced matrix looks like. And our variables are now C1, C2, C3, C4. And our question is, are there non-trivial solutions? Well, this one, notice I've got 1, 2, 3 rows, so C4 is going to be a free choice. So we probably already know the answer. Let's give it a name, T, S, whatever. Now, what about C3? Well, this is the, oh, I did that wrong. So sorry. The C3 column has stuff in it, but C4 is equal to 0. That one does have to be 0. And what about C2? Well, this says C2 is equal to minus C3, but C3 is T. And C1 is equal to minus C3, but C3 is T. So the solutions are all the scalar multiples of -1, -1, 1, 0. Does this have non-trivial solutions? Yes, I just found infinitely many, right? So -1, C1 is -1, C2 is -1, C3 is 1, and C4 is 0 is a non-trivial solution. So, and I'm out of space, so I guess I will say continued on the back side. However, okay, continued on the back side. So there are non-trivial solutions. And the vectors are not independent. That is, they are dependent. All right, now once we went through all this explanation, but in essence, you can answer these questions rather quickly. In this case, remember, I started from this set of vectors. How did I proceed? I entered them, whoops, wrong button. I entered them into the columns of my matrix, and then I row reduced it. And then I interpreted that as solving the corresponding homogeneous system of equations. I found that there were non-trivial solutions, so this set of vectors is dependent. What would it have looked like if they were independent?
It would be 0.
Yes, I'd have only the trivial solution, which means I would see that 1's down the diagonal, right? And 0's on the right-hand side. So that is for the second part of this equation, says find a subset of these three vectors that is linearly independent. Well, by the way, you can pretty much figure it out from here. This C4 is already forced to be 0, which means that that vector is not dependent on the previous three. So as this one is set up, once you choose C3, it forces the others. So that would tell you that these three have some kind of dependency in them. And a good guess would be to just eliminate the third vector and see what happens. So I think you can do that inconveniently with a calculator. So what I would like to do is is this. Let's see, is this showing up on the screen? Okay, I'm going to take this A matrix and I'm going to store it in the B matrix. And then I'm going to edit the B. So I am guessing, and that's what it is right now. I am guessing that I could eliminate that. I could eliminate the third vector. Now, that means what I would like to do is have this column, 1, 0, 0, 1, 1, 1, and then I want to throw away that one, and I want the last vector to be 1, 1, 2. And I've almost got that. I just have to edit this last column. So that looking right, 1, 0, 0, 1, 1, 1, 1, 1, yeah, 1, 1, 2. So I've just eliminated the third vector. And now the question is, does this row reduce to the identity? It does. So I'll just write the note here. If I start with this matrix, V1, V2, I eliminated V3 and went to V4, and I take its RREF, I get the 3 by 3 identity. So V1, those are vectors, V2, V3, whoops, V4 rather, are independent. And I rather suspect there's more than one correct answer here. Probably, well, I don't just suspect it, I'm sure of it. There's another vector you could have eliminated instead of the third one, and it would also work. Okay, any question about that? Now, I want to give you some insight into why I'm not following a standard linear algebra book. I don't know of a single linear algebra book that tells you how to solve this problem. Now, maybe they're out there, but I haven't seen one. And they just give you the theory and they expect you to figure it out on your own. Well, I mean, that's great if you've got a whole semester to let the theory sink in, but we don't. You know, in a few weeks, we got to be done with this and on to differential equations. So I want to give you strategies for doing things like that. Okay, we figured out that this is dependent. How do we take out a vector to make it independent? Well, here's a strategy. It's a guess and check, but it works. Okay, I told you that a basis of a vector space is a set of vectors from the space that has two properties. Number one, it's linearly independent, and number two, it spans the whole vector space. So now we have to take care of this part. What is the span of a set of vectors? And the definition is really simple. The span of a set of vectors is the set of all possible linear combinations. So what is the span of this set of vectors? Well, theoretically, it's this. C1 times the first vector, and since I don't have much horizontal room, I'll switch to vertical, plus C2 times the second vector, plus C3 times the third vector, for all possible choices of C1, C2, and C3. That's the span. Now, the problem with that is it gives you no insight, right? I mean, it's too complex. And if a human cannot do this for 3 vectors and 3 constants, I mean, in the sense, I don't know about you, when I look at this, I don't know what that set looks like. Is that all of our 3? I don't know. Maybe it is, maybe it isn't. I have no way of simplifying this expression to get an idea of what's in the set and what's not in the set. I'd like this simple enough that if you hand me a three-dimensional vector, I can tell you, oh, that's in the set, or, oh, no, that's not in the set. And I can't do that right now. It's too hard. So now, with some exceptions, hand me the zero vector, is that in the set? Well, sure. Take this first constant, second constant, third constant to be zero. That'll work. How about 37, 19, and 21 for the entries? Is that in the set? I don't know. I could solve a system of equations to find out, but it would be nice if I had a simple way of getting that information. And I do. It comes from this theorem. The elementary row operations do not change the span of the rows of a matrix. So last time I put those vectors in as columns in a matrix. Now I'm going to put them in as rows. So I start with this. There's my first vector, 1, 0, 0. Here's my second vector, 1, 1, 1. Here's my third vector, 4, 1, 1. I would like a simplified version of this. Well, lucky for us, we can easily get one. All I got to do is take the RREF. And the reason is elementary row operations. That means like taking a multiple of one row, add it to another, exchange two rows, those things that we went over before. Those do not change the span of the rows. So if I can get the RREF, you get that by taking those using operations that don't change the span. The span of this matrix will be the same as the span of the rows of, I should say, the span of the rows of this matrix will be the same as the span of the rows of the simplified matrix. And lucky for us, we have a machine that will do that for us. So second matrix, edit. And now I'm working with a 3 by 3 matrix. Do I want to kill this? Yeah, I think so. 1, 0, 0, 1, 1, 1, 4, 1, 1, and remember to quit. Remember to error check. And now let's find the RREF. Okay, that's the RREF. So what I have just computed is this: the span of this original set of vectors. Now remember, our vectors are rows, not columns here. 1, 0, 0. 1, 1, 1. And 4, 1, 1. Is the same as the span of this set of vectors. Now, y'all are very smart people, so I do not need to tell you that throwing in the zero vector doesn't help much, right? Because if I take multiples of that zero vector and add it to my sum, how does it change the sum? Not at all. So there's no sense keeping that zero vector. And that's one of the advantages of doing this RREF. It takes out those dependencies for us. And that doesn't look like it, but it's supposed to say span. And I'm going to flip the page over. And this, by the way, I'm starting to get an idea what these look like. But if you do just a tiny little bit of algebra, you'll have the recipe down flat, and anybody can give you any matrix or any vector, and you can tell instantly whether it's in the set or not, in the span of these vectors. Okay, so what I'm going to do is I know that the span of my original vectors is the same as the span of 1, 0, 0 and 0, 1, 1. So I want to figure out what does the span of 1, 0, 0 and 0, 1, 1 look like? Well, the answer is this. The span is the set of all possible linear combinations. So that means I take something times the first vector, let's say A, and add to it something times the second vector, let's call that vector, that scalar B, and I would get this. Well, I'd have A in the first component, and I have B in the next two. So it says this, the first entry is a free choice. Anything you want can be here. The second entry is also a free choice. Anything you want can be in there. But the third entry, once you've made those two choices, the third entry is forced. It must be equal to the second. And now I can answer this question for all kinds of simple and crazy looking things. 2, 17, 17, is that in this span? Well, yeah, it follows the pattern, right? The second two entries agree. How about this? Is E pi pi, is that in the set? Yes, it is. It matches. The second and third entry are equal, and etc. You just, doesn't matter how complicated, we can tell in an instant. Okay, so this is actually a useful algorithm. How do you describe the span of a set of vectors? Well, put them in rows of a matrix, row reduce it, take the simplified rows, the non-zero ones, and you're good to go. That's as simple as you can make it. Now, if you had 17 independent vectors, you know, that's still not guaranteed it's going to be simple, but it'll be simpler than it was. Okay. Any questions?
So C2 must equal C3 then?
Yes.
Okay.
Yes. Yeah, our answer is find a simple way to express the span of this. Our answer to that question is everything in the span looks like this. Anything you want in the first entry, but the second two entries must be equal. And that's it. Once again, I do not know any linear algebra books that tell you how to do this. They give you all the tools to do it, but they sort of leave you to figure it out. Okay, it turns out that there are four vector spaces of importance associated with any matrix. There is the row space, the column space, and there are two null spaces. And I need to think about, I think what I'm going to do is skip to the example on page 8 here. This is the next page. And I will compute them for you, and then you'll see how. And it's honestly, once you see it, you'll think, oh, yeah, that makes sense. At least I think you will think that. So what I'm going to do to get started is enter my matrix. So matrix, edit, A, and this will be a 3 by 4, because that's what I'm starting with. And now I just enter this thing, 1, 2, 3, 1. 1, 1, 2, 1, 1, 3, 4, 1. And because I'm so good at making mistakes, I'm going to check 1, 2, 3, 1, 1, 1, 2, 1, 1, 3, 4, 1. Okay. Now, the first of these spaces, I'm going to do RS of A, the row space of A. And it means simply this, the span of the rows of A. Now, do we know how to get a simplified version of the span of the rows of A? Hint, yes. That's what we did right here, right? we put vectors into the matrix and said, how could we get a simplified version of the rows? Well, take the row reduced echelon form and then use that to come up with a recipe for what the span of the rows looks like. So that's what I'm going to do here. I want to find the span of the rows of this matrix, and I will do it by finding RREF first. And my calculator will bail me out. And it looks like this. 1, 0, 1, 1 for the first row. 0, 1, 1, 0 for the second row, and then a row of zeros. And once you've seen the trick, you know what I'm going to do is take A times the first row and add B times the second row. I'm not going to bother with the third row. It won't add anything anyway. And my span is any vector that looks like this. I'll pick up an A in all but the middle entry. And I'll pick up a B in the second and third entries where A and B are real numbers. That's the row space. How did I get it? I row reduced the original matrix. Okay, now, number 2, find the column space of A. How do you do that? Well, the column space of A, it means basically the same thing as row space, except you work with columns instead of rows. So it's the span of the columns of A. Okay, well, how do I get a simplified version of the columns of A? Well, what I would like to do is, this is the row reduced echelon form. I would like the column reduced echelon form, but unfortunately there is no such thing. Could we somehow trick our calculators or Octave into working with the columns instead of the rows? You got it. Take the transpose that switches, that switches the columns and the rows. Then you take the RREF of that, and you could just read those rows, or you could take the transpose back. That would be fine too. So let's go for that. Second matrix, I have this in A, right? So I want to get A, and I just want a copy of it I can work on. So store that in B. Oops, wrong. Oh, shoot. Okay, got a copy in B. And now I would, I should have taken the transpose while I was doing it. Okay, well, it's no big problem. Matrix B, take the transpose. And you probably could do this all in one fell swoop, but I'm not going to. Confusing enough as it is. So I'm going to transpose it and store it back in B. Okay. So there's my transpose matrix. And now I want the RREF of this. And I think the calculator is going to give up but I'll show you how to fix it. I think that's what's going to happen. Yep. Invalid dimension. What? You can't find the RREF of a 4x3 matrix? And the answer to that is correct. With a Texas Instruments calculator, you can't. But the reason it doesn't like it is because there's more rows than there are columns. Well, what I'll do is just add a column of zeros, which will get it past what's bothering it. And that column of zeros will just stay a column of zeros, and I can just ignore it. Okay, so that's the trick. So we're going to quit. Go to Matrix, Edit B, and now I'll make this a 4x4. Oh, that did it. It filled that out with zeros already. So I can quit. And let's just verify. Everything should be fine, but sure. That's my matrix B back again. Only now I've tacked on a column of zeros there. And now when I ask it for the RREF, it works. So now you could read it this way and you would just be reading the rows, right? Or if you wanted to, just because you'd be looking at columns and the question was about columns, you could take the transpose again, but I think it's hardly worth the bother. We can get the information out of it now. So the span of the columns of A is the same as the span of these simplified columns, 1, 0, 2, 0, and 0, 1, minus 1, 0. And we all know the drill now, right? So how could we describe that with a formula? Well, you'd say something like, well, you take A times the first plus B times the second, you add them up, and that will give you a formula. We'll get A in the first entry. We'll get B in the second entry. We'll get 2A minus B in the third entry, and we get 0 in the last one. Okay, that's column space. Now, the last one is null space of A. What's the null space of A? The null space of A is the set of solutions of the system AX equals 0. The homogeneous system of equations. Well, the way we would solve that, of course, is we'd start with the matrix A. We'd probably, if we were doing it by hand, throw on some zeros there. We'd take the row reduced echelon form, and we'd look at that simplified matrix, and we would read off our answers. Lucky for us, though, we already have computed the row reduced echelon form of A. So I don't actually have to do any more calculations. I just have to reinterpret the one that I did before. So it's the set of solutions of this homogeneous equation, and there are 4 variables, and we'll be solving for x1 and x2. x3 is not specified by this, nor is x4, so those are both free choices. S and T, and X2, I call that X1. Okay, so X1 is equal to 0 minus X3 minus X4, which is the same as minus S minus T. X2 is equal to 0 minus X3, which is minus S, and X3 is S, X4 is T. And well, there's your simplified form right there, right? It's just exactly like this, except we've used S and T instead of A and B. So that's the null space of A. The other fundamental space is the null space of A transpose, but you do it the same way. You just, as a matter of fact, it's in our calculator already. You transpose the matrix A, and then you do this process again. Okay, so
you have to transpose it first?
yes, transpose first, then row reduce. And I think I have that in the calculator. Actually, let me think about it. Did I write it somewhere already? I didn't. Compute RREF of A transpose and interpret as a system of homogeneous equations. Same as we did here, like that. I'm thinking that probably about now you are beginning to catch on to my hesitancy to assign a hand-in homework for Tuesday. Yeah, right? It takes some time to work with these and get used to it. So here's what I expect. You're going to go home and work on this stuff. Some of it, you'll just do it. It'll be fine. You'll look at the notes and be able to figure it out. Other things, you just plain get stuck. Well, make a list of the things that are getting you stuck, and then I'll help you on Tuesday, okay? But honestly, that is way more efficient than me trying to think of every possible thing that could possibly confuse everybody and then go over all of that in class, because I end up answering 2/3 of the questions I answer are questions you were not going to ask anyway. So it's much better if you ask the questions, if you drive it rather than me. Okay, now let me show you a couple of examples. And by the way, these things are thrown in here because they're like homework, and they're thrown in here because they're the kind of questions people ask practically when they're using linear algebra to solve real problems, not just made up stuff. Okay, like, well, can we get to this vector right now? Well, that's a very good question. So suppose we get to work with V1, V2, and V3 as they're given here. And we would like to know, is there a linear combination of V1, V2, and V3 that equals this thing here, 3, 1, 2, 2. And I'm actually doing 2 of these because I want to show you one example where the answer is yes, and here is the linear combination that works. That's how one of these is going to come out. And the other one is going to come out to say, no, you cannot reach it. It's not in the span. Okay, so how do you tell? Well, what we do is if you think about it, we just don't have much to work with right now. We can solve systems of linear equations, right? So we try to drive everything back to that because we know how to solve linear equations, systems of linear equations. And likewise, we know how to do things with matrices, like find the row reduced echelon form and figure out what the null space is and stuff like that. So we always want to manipulate everything to something like that. So is there a linear combination C1V1 plus C2V2 plus C3V3 that is equal to the vector, and I'll stand this one up, 3, 1, 2, 2. The question is, can we solve this? Well, if we did, we would have C1 would multiply the column vector 1, 0, 1, 1. C2 would multiply the column vector 1, 0, 1, 0. And C3 would multiply the column vector 1, 1, 0, 0. Now, you could write that in this kind of a form, but you could also write it with matrix multiplication. If I take C1, C2, C3, and you just think, well, how would you do that multiplication? The C1 always wraps around and multiplies things in the first column. The C2 multiplies the second column, C3 multiplies the third, and it has to add up. If we can find a solution, it has to add up to this. Now, you can state that in terms of finding a row reduced echelon form by saying, well, you'd have your coefficient matrix. And then you'd have the right-hand side, 3, 1, 2, 2. And then you'd find the RREF of this thing. And from that, you could read off the solution, or you could read off that there is no solution, right? What would be, if there's a solution, it'll look like this. You have a 1 down the diagonal, and you'll have numbers over on the right, and those numbers will be what C1, C2, and C3 need to be. Because this is the C1 column, this is the C2 column, this is the C3 column, this is the right-hand side column. So there is no C4. So we have more equations than we do variables. So there certainly is the possibility this is over-determined. Okay, well, let's see. Matrix edit, and this is going to be a 4x4. So 1, 1, 1, 3, 0, 0, 1, 1, 1, 1, 0, 2, and finally 1, 0, 0, 2. Okay, now let's go to, let's quit. Go to matrix. I want to play this back and see if I got it right. I did. Okay, so I want the row reduced echelon form of that matrix. Matrix, math, RREF. Okay, and I'm kind of out of room here, but that's okay, because we'll be smarter about it when we get down here. We'll need less space. So the RREF of that matrix is this one, 1, 0, 0, 2, 0, 1, 0, 0, 0, 0, 1, 1, and a row of zeros. The C1, C2, and C3 columns first, and the right-hand side columns next. So what this tells me is, can we solve this system? Yes, we can. Set C1 to be 1, set C2 to be 0, and set C3 to be 1. So way back to the question, is there a linear combination of these that adds up to 3, 1, 2, 2? Answer, yes. And this is what it is. So we don't just get a yes or no. We get which linear combination works.
Isn't C1 supposed to be 2?
It certainly is. Thank you. Thank you. All right. Ready to do the next one? Now, the next one is almost instant, okay? Because notice the only difference here is I changed this 2 here. I changed this 2 to a 4. So all I've got to do is go back into my matrix menu and edit this A. And what I want to do is go to the next to the last entry in the right-hand column and change that to a 4. And did it work? Yes, it did. And now I want, oh, I didn't need to leave the matrix menu. I want the RREF of this new and improved matrix A. And this time, I get a problem. Notice that last row. That last row says 0C1 plus 0C2 plus 0C3 equals 1. That should bother you. Yeah, it's not true, right? It doesn't matter how I choose the C's, it is not true. So the RREF this time to complete the notes is this matrix, 1 followed by 3 zeros, 1 0 0 0 1 0, and then 3 zeros and a 1, and that's a problem. That right there is a contradiction, and it tells me there is no solution. So what that means is 3142 is not an element of the span of the given vectors. Okay. Well, we're almost out of time, but we're also almost out of material. I'm finally ready. What is the basis of a vector space? It's a set of vectors in the space that spans the whole space and is linearly independent. Okay, that's it. Now, what is the dimension of a vector space? It is simply the number of vectors in any one of its bases. It turns out that in general, vector spaces have more than one basis, but every single one of their bases has the same number of vectors in it. So you just find a basis, you count the number of vectors, that's it. You have discovered its dimension, the dimension of the space. And I could say a lot more about that, but I don't have time, and it's pretty easy to read anyway. Okay, how do you tell if a set is a basis? Well, there are 2 answers to that question. The long answer is this, and you do this sort of in a general setting where you had no other information. You just said, here's a vector space, and here's a set that might or might not be a basis. Figure out if it is. Well, you'd check to see if it's linearly independent, and then you'd check to see if it spans the whole space. If the answer is yes to both of those questions, it's a basis. If the answer is no to either one of those, it's not independent or it doesn't span the whole space, it's not a basis, okay? But we actually have one of these cool, the following are equivalent theorems, and that is this. Usually, for our purposes, if somebody asks that question, we already know the dimension of the space. So if somebody gives you vectors, they have 5 real number entries in them, well, it comes from 5-dimensional space, right? So we actually have one extra piece of information. I've got 5 vectors here. Someone hands me 5 vectors. I know they came from a 5-dimensional space. The question is, do they form a basis? Well, the answer is, if they're linearly independent and they span the whole space, then they are a basis. But there is a bonus that comes in this case. If the number of vectors you're testing is equal to the dimension of the space, if the vectors are linearly independent, they also span the space. If they span the space, they are also linearly independent. So you cannot have one without the other. So if somebody hands you n independent vectors in an n-dimensional space, it's a basis. If somebody hands you n vectors that span the whole n-dimensional space, it's a basis. It's also linearly independent. So any one of these is the same as any other. It's a basis, or it spans, or it's linearly independent. If it's one, it's all three. Okay, so it just saves work. You only have to check one of these rather than two if you have n vectors in an n-dimensional space. Now, if you're in some wild theoretical setting where you have no idea what the dimension is, well, then you're just going to have to check both of these independently. Okay, so how do I know if this is a basis for R3? Well, what I would do is I would put it, I mean, what do we always do? We put it in a matrix, right? I would compute the RREF of that matrix. Now, I don't have time to do it, but one of two things is going to happen. I'm going to have 3 non-zero rows, or I won't. If I have 3 non-zero rows, those original vectors are independent, and therefore they span the space, and they are a basis for R3. On the other hand, if I get a row of zeros, then the test failed. It's not a basis, and they are not independent, and they don't span R3. Okay, so that's the quick version on that. Okay, now I am finally ready for this, and I actually planned this part. You will notice I never formally defined a vector space. That is because it is deadly boring. Basically in this class, we're going to be working with Rn, the whole darn course. So these are automatically all true of Rn for any n, okay? And if you just read through the list, you'll look at it and say, oh yeah, of course, of course. Now, if we were doing abstract linear algebra, I would have to go through this in real detail, but we're not. We're doing linear algebra for use. So I'll ask you to read this so I can, in good conscience, say if someday the chairman of the math department says to me, "Are you sure you told them the definition of a vector space?" I can say with a clear conscience, "Yes, sir, I did." As a matter of fact, it's in my notes. So that's what a vector space is. Examples of real vector spaces, we've already given a bunch of them. And let me just give you one, though, that doesn't look like what we've done before. What if we had this set of functions? A0, some constant, plus a number times x, plus a number times x squared. It's the quadratic polynomials, right? Notice how that aligns with this vector. The polynomials of degree 2 and less form a 3-dimensional vector space. So you've been working with vector spaces for ages. And if you think about it, in high school, that was one of the big hurdles to get over. Oh, when I add 2 polynomials, I just add up their coefficients. Why? You were adding 2 vectors. No one told you, but that's what you were doing. Oh, when I multiply a polynomial by 2, what do? Well, I double all the coefficients. Why? Because that's how you do scalar multiplication. Just nobody told you. Now you can go back and say, why didn't you tell me that? And they'll say, because you weren't ready. Unless of course you have a math teacher who was a math minor rather than a math major, and they said, what? And you can explain it to them. Okay, that's all there is to say about that. And now there is a substantial amount of information on subspaces. I am going to have to save this till Tuesday because that does take a little bit of time. But just know we've actually already done it. I did it tonight. It's at the very beginning of the lecture, but I didn't tell you that's what I was doing. So it's just like you were tricked in high school. You know, you do all this stuff with polynomials, and then a few years later, someone says, oh yeah, you were just doing a vector space. So on Tuesday, I'm going to say, remember the stuff we did way back here with closure? We were solving problems for subspaces. So, but I do not have time to do that in adequate detail. As a matter of fact, I may not have done anything with adequate detail tonight. This is pretty fast. But it has to be, because we need to get on to differential equations as soon as we can. So my advice to you is do everything in homework that you possibly can. Come on Tuesday with a list of questions. If you will be attending by Zoom, if you would like to email in your list of questions, that would be fine too. And then I'll have something to work from. All right, I wish you well. Have a great weekend, and I'll see you next week.
Are we gonna be doing a lot with infinite series?
No, well, we do have one unit where we work on those, yes.
That was the thing I struggled with the most in Calc 2, probably because it wasn't really explained that well.
It's probably because it's a brand new idea. And it
Like, I
takes.
get the concept of what they are, but I guess doing like integrals and